Hello, welcome to lecture 7 of parallel computing. So in the last lecture, we looked at how to use the collective communication operations in MPI to solve certain problems. Okay, so today we're going to look at how to efficiently implement these collective operations. So now we know these operations are used in many parallel algorithms because many of these algorithms require communication between groups of processors. Now, there are different ways to implement these collective operations. For example, you can implement them as simply by doing many point-to-point communications. Okay, but it turns out that there are often more efficient methods to implement these operations by using parallelism. Okay, so we have parallel communication algorithms which work faster. Now, first of all, before we talk about these algorithms, we're going to define a cost model for communication. And this is going to go back to the model that we talked about a few lectures ago, where we talked about communication in networks. And so there we said that in order to send a message of size m, okay, there are basically two parts to this cost. So first, you have to do some startup operations before you can send the message. And this has time ts, okay? And next, for each word that you send, right, let's say that you pay a cost of tw time. Okay, so it takes you tw amount of time to send a word. And if we want to send m words, then the time is just m times this. Okay, now notice that in this cost, we're ignoring the distance that the message travels. Okay, and the reason is that even though for each hop the message goes through, we do have to pay a latency cost of, let's say, th. This value th is usually small compared to the ts and the m times tw terms, and so therefore we're going to ignore the th terms. Okay. Also, if we have contention when we're doing the sending, okay, so if the contention is C, then that means that there are C processes trying to send through the same link. Okay, so if each of these processes tries to send m words, right, then the time for all of these sends is now going to be basically this expression over here. Okay, so we'll look at how to implement these collectives, but this depends on the type of communication architecture that you have. Okay, so for example, the amount of time to do these operations in a ring network versus a mesh versus a hypercube may be different. Okay, so we're going to look at these operations and we're going to look at their cost in various communication architectures. And the operations we're going to look at include these ones, okay? The broadcast and reduction operations. We're also going to look at all-to-all broadcast and reduction, okay? We have all reduce, prefix sum, scatter and gather, and we also have all-to-all scatter and reduce. And then we're going to look at a circular shift. Okay, so we're going to start out with the broadcast algorithm on a ring. Okay, so here what we're trying to do is suppose one process in the ring. Okay, so suppose you have a ring of p processes, and one process starts out with a value, and it just wants to give this value to all of the other processes. Okay, so of course one way to do this is just this process, let's say process 0, can just send individual messages to all of the other processes. Okay, so if there are p other processes, then this would basically take p minus 1 amount of time. Okay, so this is quite slow. And the reason is that this kind of broadcast is basically doing a sequential type algorithm, right? Because process 0 is doing all of the work. Okay, so instead, we want to have a parallel algorithm for doing the broadcast. Okay, and the way we can parallelize this is that we're going to have process 0 send the message to other processes. And once these other processes get the message, then they can help process 0 do the broadcast. Okay, so the way this is going to work is if we're on a ring of size p, right, then we're first of all going to send the message a distance of p over 2. Okay, so halfway around the ring. Okay, so this means that, so let's say that initially process 0 has the value. Okay, then in the first time step, he's going to send the process to, the value to process 4. Okay, so so the way we indicate that is with this this dotted line over here, and the 1 indicates that this is the first step of the algorithm. Okay, so after the first step, right, process 4 also has the value. Okay, so now we have somebody else to help process 0 do the broadcast. Okay, so next we're gonna send the message again, but now there are 2 processes that can send the message, right, 0 and 4. And the distance that we send is going to be half of the previous distance. So the first time we sent a distance of p over 2, and so this time we're going to send a distance of p over 4. Okay, so that means that 0 is going to send to 2, right? So now 2 is going to have the message, and 4 is going to send to 6, and so 6 has the message. Okay, so you see that there are these 2 dotted lines marked by the 2, indicating that this is our second step. Okay, so now after the second step, you have 4 processes that have the message. Okay, so then we're going to do one more step where all of these 4 processes are going to help send the message, and the distance that they send the message is again going to be half of the previous distance, right? So previously you sent a distance of 2, and now we just send a distance of 1. Okay, so by doing this, you see that all of the processes 1, 3, 5, and 7 will get the message. Okay, so now we've successfully broadcast the message. Okay, so that is how we do the broadcast. So next we want to do a reduction. Okay, so reduction, what we're trying to do here is that so we have a ring, and suppose every process in the ring has initially some value. Okay, and now we want to take all of these values and reduce them onto, let's say, process 0. Okay, so reduce means to just add up all of the values. So we're going to do a sum reduction here. Okay, now if you think about it, the broadcast and the reduction are kind of opposites of each other, right? So broadcast, we're trying to send the value to everybody else, and reduction, we're trying to collect values from everybody else. Okay, so because these 2 operations are opposites of each other, then the way we're going to do the reduction is, in fact, we're just going to reverse all of the communication that happens in the broadcast. Okay, so now remember the final step of, so the final step of the broadcast is going to become the first step of the reduction. Okay, and remember in the final step of the broadcast, right, you had 4 processes that sent messages a distance of 1. Okay, so we're going to take these 4 messages that are marked by the 3, and we're just going to reverse them and make these into the first step of our reduction algorithm. Okay, so when you do this, so for example, 7 is going to send a message to 6, and when 6 gets that message, it's just going to add its own value to 7's value. Okay, so the way I'm going to indicate that is, so 6 is going to basically add its value to 7's value. Okay, and 4 is going to get a value from 5, so it's going to add those together. Right, 2 is going to get a value from 3, which it adds, and then 0 gets a value from 1. Okay, so that's step number 1. And now for the next step, now we're going to send the message a distance of 2. Okay, so 6 is going to send to 4, and 3 is going to send to, 2 is going to send to 0. Okay, and when this happens, 4 is going to add the value it gets, which is 6 plus 7, right? Because 6 now has the sum of 6 and 7, so it's going to send that sum to 4, and 4 is going to add it to its own sum. Okay, and likewise, 2 is going to send to 0, so then 0 is going to end up with the sum of the values from 0 to 3. Right, so that's going to be the second step, and the final step is that we're going to send the value a distance of 4, right? So then, so then 4 is going to send its value to 0, and 4 is going to send the sum of 4, 5, 6, and 7. Okay, and when 0 gets that, it's going to add in all of those values, and then 0 is going to end up with a sum of all 8 values. Okay, so that is the broadcast and reduction algorithms. Okay, so next we're going to look at the cost, the time complexity for running this algorithm. Okay, so so the cost, so if you have P processors, then the number of steps that you have to take is that when you think about the broadcast algorithm, right, each time you double the number of processes that have the value. Okay, so therefore, after log P steps, all P processors have the value, and then we can finish. Okay, so these algorithms run for log P number of steps. And in each step, you could have several processes send messages, but they're all sending in parallel. Okay, and all of the messages are size M, right? Because, for example, in the broadcast, the only message you send is process 0's value, which has size M, let's assume. Okay, and likewise in the reduction algorithm, right? The only thing you're sending are the sums of the values that you received, right? So that's just, so you can represent that sum by a single value of size M. Okay, so so in total, we're taking log P steps. Each time you're sending a message of size M, so therefore the, and the time to send that message is just TS plus M times TW, right? And you multiply that by the number of steps, and this is your total time complexity. Okay, so that is broadcast on a ring. So next, let's move to broadcast on a mesh, on a two-dimensional mesh. Okay, so so the way we're going to do this is just like a mesh generalizes a ring, right? Then we're basically so a mesh is just like a two-dimensional ring. Okay, so therefore we're going to apply the ring algorithm on the mesh, but we're going to apply it in both dimensions. Okay, so concretely, what I mean by that is if you want to broadcast, okay, then first of all, we're going to broadcast on the row. Okay, so so initially 0 has the value, and it's first of all going to broadcast on its row. Okay, and to do that, right, it needs to send the message halfway across the row in the first step. Okay, so in step 1, 0 is going to send to 8, right? So now both 0 and 8 have the value, right? And then on the second step, both 0 and the 8 are going to send simultaneously a distance of 1. So then after that, let me draw these a bit nicer, so I can't really put my hand flatly on my computer. So anyways, so you have a 0 and you have a 4, okay? And then 12, okay? So all of these, have the value now, okay? Okay, so now this entire first row has the value, okay? And now we can use, now we're going to broadcast along the columns. Okay, since everybody, every node in the first row has the value, then we can have all of these processes in the first row broadcast on their columns in parallel. Okay, and the way the broadcast works is, since we have 4 nodes on each column, then they're first going to send the value a distance of 2. Right, so in the third time step, we're gonna all 4 nodes are gonna send the values a distance of 2, right? So then 2, 6, 10, and then 14 are gonna have these values, right? And then finally on the fourth step, right, everyone's gonna send the value a distance of 1. Okay, and then after that, you see that all of the nodes have the value. Okay, so the mesh algorithm is basically you do several copies of the broadcast algorithm on the ring. Okay. All right. So so then what is the cost of doing this? Well, previously we saw that the cost for broadcasting on the ring is this involves log P, where P is the number of processes that are taking part in this broadcast. Okay. Now, for the mesh algorithm, the first thing we needed to do was to broadcast along the first row, right? So the number of processes we have is going to be, so this is going to be, if we have P processes in total, then the mesh has size root P by root P. So therefore, to broadcast along the first row, right, this is going to take log of root P number of steps. Okay, so and this is equal to log p divided by 2 number of steps. Okay, and then after that, we were going to broadcast on the columns, and this also takes log of root p steps. Okay, so again, that's going to be log p divided by 2. Okay, and each of these broadcasts, each time you send a message, it takes you time ts plus m times tw. Okay, and you do this for log p divided by 2 steps along the rows, and then log p divided by 2 along the columns, right? So altogether, you add these, and then the total time you get is going to be this expression over here. Okay, and this turns out to be actually the same amount of time as broadcasting on a ring, right? It's ts plus m times tw times log p. Okay, so next we're going to look at broadcast on a hypercube. Okay, so on a hypercube, we're going to take the same approach, basically, meaning that we try to parallelize this broadcast operation by recruiting other processes to help node 0 do the broadcast. Okay, so the way we're going to recruit processes is that a hypercube, you can very naturally think of this, you can decompose the hypercube in a hierarchical way, right? Because remember, the way that we built the hypercube was that you kept on taking lower dimensional hypercubes, right? You took a pair of lower dimensional hypercubes and you connected them, okay? So now if you want to split the hypercube, you can just disconnect these 2 lower dimensional hypercubes. Okay, so what we're going to do is initially node 0 has the value, right? And now we want to basically decompose this problem by saying that we want 0 to broadcast to all of the nodes, okay? But that's equivalent to 0 broadcasting on this forward phase, and then 0 also broadcasting on the back phase, okay? So now how do we get 0 to broadcast onto the back phase? Well, we have 0 send the value to its neighbor in the back phase, which is 4. Okay, so in the first time step, right, 0 is going to send to 4. And now once this happens, right, then you've basically you've broken this problem into 2 parts. One on the front face, right, and then one on the back face. Okay, all right, so now we continue with this, and so on the front face, right, we again want to break the problem into 2 halves. So you want to break these 4 nodes into 2 halves consisting of these 2 nodes and then these 2 nodes. Okay, and likewise on the back face, you want to do the same thing. You want to break these 4 nodes into these 2 lower dimensional hypercubes. Okay, so then how do you do that? Well, all you need to do is have 0 send its value to 2. Okay, and 4 is going to send the value to 6. Okay, so then after this happens, then 0 doesn't need to worry about broadcasting to nodes on the top half anymore, right? It can just focus on broadcasting to nodes in the bottom half. Okay, and likewise 4 can focus on the bottom half, and 6 is going to take care of the top half. Okay, and so in the final step, you have all these processes broadcast to the other half of their smaller hypercube. Okay, so 2 sends to 3, and then 0 to 1, 4 to 5, and 6 to 7. Okay, and then after this happens, all of the processes have the value. Okay, so now let's look at the cost for doing this. So again, there are going to be log p steps, right? Because if you have p processes, then the hypercube basically has log p dimensions, right? And you notice that we had to do 1 broadcast for every dimension, right? So yeah, so therefore the total number of steps is log p. For each step, you had to send a message of size m, so that takes you this ts plus mtw time. And so again, the broadcast time is going to be this term. Okay, it's the same as for broadcasting on the mesh and on the ring. Okay, so next we're going to look at the problem of all-to-all broadcast on the ring. Okay, so all-to-all broadcast, what I mean by this is that every process wants to do a broadcast. Okay, so 0, for example, process 0 has a value, and it wants to send this value to all the other processes. Okay, likewise, process 1 has a value, and it wants to send that to all the other processes. Okay, so every process starts with a value, which it's a single value. Okay, and it wants to send that single value to all of the other processes. Okay, so the way that we can do this is that the way that 0 can broadcast is you can imagine that 0 can take its message and just send it all the way around the ring. Okay, just sort of pass the message all the way around the ring. Just node by node, it can pass its message around the ring, right? So that would take p-1 steps because there are p nodes in the ring. Okay, and likewise, node 1, if it wants to do a broadcast, right, it can also take its message and also pass it all the way around the ring. Okay, and node 2 can pass its message all the way around the ring, and so on. Okay, so the way this algorithm is going to work is that we're going to have all of the processes do this sort of message pass their message around the ring. Okay, and it turns out that all of them can do this passing process simultaneously. Okay, and in parallel. Okay. And the reason is that, for example, when 0 wants to pass its message around the ring, right, it's first going to send to 1. It's first going to send to 1, right? And likewise, when 1 wants to pass its message around the ring, it's going to first send to 2, okay? And then 2 is going to send to 3, and so on, okay? So you see that the first step of all of these broadcasts, they're going to use different links. Okay, 0 is going to use the link between 0 and 1, and 1 is going to use the link between 1 and 2, and so on. Okay, so none of these, so all of these sending these messages, all of them, none of them conflict with each other. Okay, now on the next step, 0's message is then going to go from 1 to 2, right? And 1's message is going to go from 2 to 3, and 2's message is going to go from 3 to 4. Okay, so then again, these messages are not going to conflict with each other because they're being sent on different edges. Okay, and so so therefore you can see that what we'll do is we'll just have all of the processes send their messages in p-1 steps around the ring, and none of these steps conflict with each other because at every time step we're going to be using completely different edges. Okay, and so this is illustrated in this picture over here where, let's see, yeah, so these values, these are like the ones over here are indicating that this is step 1 of the process. Okay, and then this the values in the parentheses are indicating which value is being sent. Okay, so for example, this 0 means that in step 1, process 0 is sending its value to process 1, okay? And also in process step 1, process 1 is sending its value to process 2, which is sending its value to 3, and so on. Okay, and now also these numbers in the parentheses at the nodes, okay? So these are indicating which values a node has already received. So initially, every node just has its own value. So initially, you know, it only has its own value. But after you take one step, right, then for example, 1 has received 0's value. Okay, 2 has received 1's value, 3 has received 2's value, and so on. Okay, and then on the second step, what value are we passing? Well, on the first step, so for example, 0's value went to 1. So on the second step, 0's value is going from 1 to 2. Okay, and 1's value is going from 2 to 3, and so on. Okay, so so we just do this. We keep doing this for p-1 steps, and eventually all of the processes are going to end up with all the values. Okay, and in each time step, the amount of time, or sorry, in each communication step, the amount of time we take is this ts plus mtw term, and we're going to take p-1 steps. So so that is the total amount of time. Okay, it's basically linear in the number of processes. Okay, so next we're going to look at all-to-all broadcasts on a torus. Okay, so torus is just it's a 2D mesh, except for the first and the last processes in each row and column are connected. Okay, so yeah, so let's see. Okay, so to do this broadcast, right? What we're going to do is we're first going to broadcast. All the nodes are going to broadcast are going to do all-to-all broadcast, okay, on the rows. Okay, so for example, the first row of processes, which are 0, 1, 2, they're going to do all-to-all broadcast. Okay, if they do all-to-all broadcast, then after this, right, they're all going to, all of these processes will get all of the values from the first row. So for example, 0 is going to have value 0, 1, 2, right? 1 is also going to have value 0, 1, 2, and so on. Okay, and also we're going to have the processes in the second row also do all-to-all broadcast. So they're all going to end up with values 3, 4, 5. Okay, and then the processes on the third row, they all do the all-to-all broadcast. So they all get values 6, 7, 8. Okay, so now we've successfully broadcast along the rows. And then the next thing to do is to broadcast along the columns. Okay, so now if you broadcast, if you do all-to-all broadcasts along the columns, right, then that means that, for example, the values over here on the first column, right, all of these are going to end up at 0, right? And yeah, so basically, if you do all-to-all broadcasts on the first column, right, then all of the processes will have all 9 values. Okay, and likewise, all the processes on the second column will have all 9 values, and same for the third column. Okay, so that's the algorithm, is to basically do two phases of all-to-all broadcast. Okay, in parallel, and each phase does multiple all-to-alls in parallel. Okay, so now the cost. Okay, so the cost is well, the first stage, right? So if you have p processes in this torus, then again it's going to be a root p by root p torus, right? So we saw that if you want to do all-to-all broadcast among, let's say, k processes, it takes you time proportional to k. Okay, so here we only want to do broadcast along a row of root p processes. So therefore, the cost is going to be this this expression times root p minus 1. Okay, so that's the first stage to do all of these row-to-row broadcasts. Sorry, the row-wise all-to-all broadcasts. Okay, and then next you need to do the column-wise broadcast. However, when you do the column-wise broadcast, right, you're actually sending these messages of size root p minus 1. Okay, so for example, 0 wants to broadcast not just one value, but all 3 values to its column. Okay, 3 is also broadcasting 3 values, and 6 is broadcasting 3 values. Okay, so in general, we're actually sending root p values, right? Because we're taking all of the values from the first from each row, and they're root p such values, and then you do the broadcast. Okay, so therefore, the messages actually have size m times root p. Okay. And to do the broadcast, again, since you're broadcasting on the column and there are root p nodes on the column, right, then the number of steps this takes is going to be root p minus 1 times the amount of time for each send, right, which is this m times root p times tw. Okay, so then now you multiply everything out and you simplify, and you get that the overall broadcast time is something like m times tw times p minus 1, okay, plus this other term over here. Okay, so now next let's talk about all-to-all broadcast and also reduce on the hypercube. Okay, so on the hypercube, what we're going to do is yeah, so we're going to do, so the hypercube of p processes has log p dimensions. Okay, so we're going to solve the problem along each dimension one by one. Okay, so it's basically going to take log p steps. So now in each step, right, we're going to pick one of these dimensions that we haven't processed yet, right, and we're just going to exchange all of the data along that dimension. Okay, so in fact, we're going to go in the dimension. We know that all of these processes can be represented by binary numbers. Okay, with log p digits. Okay, so we're basically so the dimensions that we have, we're gonna go in the dimensions of the digits. Okay, from the least significant digit to the most significant digit. Okay, so first of all, we're gonna go in the ones digit, right? So for example, 0 is gonna broadcast to 1, and 2 is gonna broadcast. 0 is gonna exchange with 1, and 2 is gonna exchange with 3. Right? So you see that all of these exchanges are between processes whose ID differs by 1. Okay, and then in the next step, we're going to go in the dimension corresponding to the second most significant digit. Right? So then 0 and 2 are going to do exchanges, 1 and 3, 4 and 6, and 5 and 7. So you notice that all of these IDs differ by 2. Okay, and in the third phase, we're going to go with the third digit. So all the exchanges are between processes whose IDs differ by 4. Okay, and then if we had more dimensions, the IDs would differ by 8, 16, and so on. Okay, so they keep doubling. Okay, now when you do these exchanges, all you're going to do is each process is going to take all the data that it currently has, okay, and send it to the other process, okay, to exchange it with the other process. So for example, initially, each process only has its own value, right? So when they do these exchanges, right, they're just going to, collect both of these values. So then 0 is going to end up with value 0, 1. 1 is also going to end up with 0, 1, right? So 4 and 5 do their exchange. So they both get the values 4, 5, and so on. Okay. And then next, we wanted to do exchanges between like the 0, 2 processes, 1, 3, 4, 6, and so on. So for example, when 0 and 2 do the exchange, right, they're going to collect all of their values. Okay, so 2 is going to get these 0, 1 values, right, and then 0 is going to get the 2, 3 values from 2. Okay, and then afterwards, both processes are going to have all 4 values. Okay, and likewise, when 3 and 4 do their exchange, right, they're also going to have the first 4 values. Okay, 6 and 7 are, 4, 6, and then 5, 7, they're all going to end up with the values 4, 5, 6, 7. Okay, and then on the final step, right, we're going to do exchanges in this in the dimension corresponding to the highest significant digit, right? And then after you do that, you see that all of these processes are going to have all 8 values. Okay, so that's the algorithm. The number of steps you take is equal to the number of dimensions, which is log p. Okay, and now in the ith step, right, you see that the size of the messages that we're sending keeps increasing, right? In fact, it doubles every time, right? So initially you had you're sending messages of size 1, right? And then next you're going to send messages of size 2, and then 4, and then 8, and so on. Okay, so in the ith step, you send messages of size 2 to the I. Okay, so therefore, the total number of the total cost would be that. So we have log p stages, but the stages have different cost. Okay, so the ith stage has a cost of 2 to the I minus 1 times tw times m plus ts. Okay, so so if you add this up, then this is a geometric series, and the sum of this is going to come out to this value over here. Okay, so that is the all-to-all broadcast on a hypercube. And then the all-to-all reduce, okay? So this is actually gonna, so all-to-all reduce means that every node starts with a value, right? And at the end, you want to have every node know the sum of all of the values, okay? And to do this, you can do this by just having all of the nodes broadcast all their values. Okay, so if you do an all-to-all broadcast, okay, then you can get the answer for the all-to-all reduce by doing the all-to-all broadcast. Okay. However, when you do the all-to-all broadcast, when you get a value from another node, right, you can just add that value to your own value. Right? You don't need to keep your own value and the other node's value separate. Right? You can just add them together because in the end, you just want to add together all the values. Okay, so for example, here, when 0 and 1 do their message exchange, right, in the all-to-all broadcast, they each had to keep two different values, right, 0 and 1. Okay, but if we're trying to do the reduce, then you don't have to keep both values. You can just do 0 plus 1. Oh, oops. Okay, you can do the 0 plus 1 and the 0 plus 1 over here. Okay, and 2, for example, would add its own value to 3's value. Okay, and 3 would do the same thing. Okay, so now on the next step, right, when you do the exchange between 0 and 2, right, you don't need to send two values. Okay, you don't need to send 0 and 1 separately. You just send the sum of 0 and 1. Okay, and likewise, 2 is just going to send the sum of 2 and 3 to 0. Okay, so you're sending just a single value. Okay, so you're still going to go through log p stages, but now you don't have this issue that the messages keep getting larger. Okay, the message that you're sending is always just going to be one value, which is equal to the sum of all of these values that you've received so far. Okay, so therefore the cost is going to be, we have log p stages, and in each stage you just send one value, and so the amount of time that you take is going to be this. Okay, which is a lot less than the cost to do the all-to-all broadcast. Okay, so next we're going to look at how to do prefix sum on the hypercube. Okay, so remember that the prefix sum operation was if you have a bunch of processes, let's say you have processes 1, 2, 3, 4, right? And so they're going to start with some values. Okay, so suppose that process 1 starts, so the values are down here. Suppose it's got a value of, let's say, 3 initially. Okay, this has a value of 1, this has 5, and this has, let's say, 3. Okay, right. So then the prefix sum is the ith process should get the sum of the first I values. Okay, so then the prefix sum, right, is going to be that the first process is just going to get the sum of the first value, which is 3. Right. The second process is going to get the sum of the first two values, which is 4. Right. Third process gets the sum of the first 3 values, and that's going to be 9. And then the fourth process gets 12. Okay, so that's what we want to have happen. Okay, so now to do the prefix sum, right? So this is illustrated in this figure over here, and what we have is that each process is going to maintain 2 values. Okay, and the values are shown both in the parentheses and then in the brackets. Okay, so the values in the brackets are actually the prefix sum that the partial prefix sum that this process has computed. Right, so the process is supposed to end up with a prefix sum. Okay, so it's going to build up towards that. So it's going to have sort of a subset of the prefix sum as it executes the algorithm. Okay. And then the value in the parentheses, this is supposed to be the sum of all of the values that the process has received so far. Okay? Now, I should point out that there's some mistakes in this figure. Okay? There are a few mistakes. So, for example, in let's see, in figure B, right? This 6 value over here, okay, the one in the parentheses. So this should actually be 6 plus 7. Okay, so this should actually be 6 plus 7 here. Okay, and another example is let's see. So so in figure C, right, this 4, 5, 6 over here, right? So this should actually include the 7 also. Okay. All right, so it's kind of bad, but let me write this 4, 5, 6, 7. Okay. Right, and there are a few other mistakes, but basically the figure is correct. Okay, and so now let's see what these figures are showing. So the way this algorithm works is that So this is going to be similar to the all-to-all broadcast algorithm, okay? In the sense that we're going to work in these different dimensions, okay? We're going to go through all of the log p dimensions one by one, right? And we're going to go through them in the order of least significant digit to the most significant digit for the IDs of the processes. Okay, so the least significant digit would be this direction, where all of the processes differ by 1. Okay, and then the second most significant digit would be where where all of the processes that communicate where their IDs differ by 2, right? And then the final dimension, so their IDs are going to differ by 4. Okay, so we're going to go through the dimensions in this order. Okay, and for each dimension that we process, what's going to happen is the processes in that dimension are going to exchange their values. However, the process is going to when you do an exchange between these two processes, they're both going to send this sum value that they have. Okay, so remember the sum values are the ones in the parentheses. Okay, so if 6 and 7 do an exchange, right? So maybe let's go for a different one over here. Okay, so when 4 and 5, so which one should I? Okay, so how about this one? Okay, so for example here, when 0 and 2 do an exchange, okay, so then 2 is going to send the sum of 2 and 3, the sum of 2's value and 3's value, right? And then 0 is going to send the sum 0, 1 over here. Okay? Yeah, so they don't send the values in the brackets, right? So the bracket values are the prefix sum values, right? They don't send those, okay? Instead, they send the values in the parentheses, which are the sum values, the sum of all the values that they've seen so far. Okay, so you see that after this exchange, for example, right, then 0 is going to end up with the sum is going to be now the sum of all the first 4 values. Okay, and then likewise for 2, he's going to get the sum of the first 4 values. Okay, now what about these prefix sum values? Okay, so the way the prefix sum values are going to be modified is that if a process gets the process is going to receive some sum values. Okay. Now, if these sum values correspond to values from processes with lower IDs, okay, then this process is going to add those sum values into its own prefix sum. Okay. So as an example, when 2 gets a message from 0. Okay, so the value it gets from 0 is going to be the sum of processes with lower IDs than 2. Okay, so then 2 is going to add these values into its own prefix sum. Okay, so 2 is going to take its current prefix sum and then add 0 and 1 to this. Okay, and then it's going to end up with this prefix sum over here. Okay, on the other hand, when you're receiving this sum value, and these sum values come from processes with larger ID than yourself, okay, then you don't add those into your prefix sum, right? Because if you have a certain ID, right, then your prefix sum should only include values from lower ID processes, right? So for example, when 0, right, it's going to get this sum of 2 and 3 from process 2, okay? But because 2 and 3 have higher ID than 0, right, then 0 is not going to add 2 and 3 into its prefix sum. So therefore, it's going to keep its prefix sum at 0. Okay? Yeah, so, okay, so then that's how this algorithm works. Okay, so the reason that this algorithm works correctly, okay, is because, basically, if you look at this sum part over here, okay, so what's going to happen is after you run this process, this algorithm for a certain number of steps, right, then each of the processes would have computed part of its prefix sum. Okay, so for example, at the start of this step, right, then the processes in, let's say, the back phase, okay, so that's like 4, 5, 6, 7, right, they've already computed part of their prefix sum. So for example, 4, all right, it's computed just, a single value from its prefix sum, okay. 5 has 2 of these values, 6 has 3 values, and then 7 has 4 of these values. Okay. Now you notice that the only values missing from the prefix sums of these 4 processes, from 4, 5, 6, 7. Okay. The only values missing are the sums from 0, 1, 2, 3. Okay, because if you add the values from 0, 1, 2, 3 to these prefix sums, right, then these become the correct values. Okay, so now in the third step, right, we actually do this exchange between the front face, between the 0, 1, 2, 3 processes and the 4, 5, 6, 7 processes. Okay, and the value that this front face is sending is exactly the 0, 1, 2, the sum of 0, 1, 2, and 3. Okay, so in effect, all of these processes in the front face have this sum of 0, 1, 2, 3. Okay, so all of them are going to send the sum of 0, 1, 2, 3 to their partner in the back face, right? And their partner is going to add in this value to their current prefix sum, and they're going to end up with the correct prefix sum. Okay, yeah, so that's why this is working correctly. And in terms of the cost for doing this, right, so what we have is that each time use, so we have log p steps because there are log p dimensions. And for each step, you're sending just a single value, right, because you're just sending this, these sum values over here. Okay, so therefore, to send that sum value, it just takes you this ts plus m times tw time, and then you do this for log p steps. Okay, right, so next we're going to look at the scatter and gather operations. Okay, so for the scatter operation, and we're going to do this on a hypercube. Okay, so, so for the scatter operation, what we want to do is now we're going to assume that process 0 starts with some values, but it has a different value for each process. Okay, so it wants to send these different values to the different processes. Okay, so in fact, it starts with 8 values, and it wants to send value 1 to process 1, value 2 to process 2, and so on. Okay, so the way we're going to do this is, again, we're going to parallelize. And we're going to have, so in the first step, 0 is going to split the problem in half. Okay, so the current problem is to send 8 values. So it's going to split this in half, and then 0 is only going to have to send 4 values. Okay, and it's going to give the other half of the problem to another process to help it. Okay, so in particular, we're going to split the values into the first 4 values and the next 4 values. And then you're going to take the second half of the problem and you're going to pass it to process 4, right? And then now you've basically split the problem in 2 because 0 can just focus on doing the scatter in the front hypercube, right? Whereas 4 can focus on doing scatter in the back hypercube, right? So 4 gets the values 4, 5, 6, 7. And now it's responsible for scattering these values to the processes 4, 5, 6, 7. Okay, and then 0 just keeps the values 0, 1, 2, 3, and it's going to scatter these to the processes 0, 1, 2, 3. Okay, so that's the first step. On the next step, we're going to split the problem again, right? So then 0 is going to just keep half of the values, the first half, and it's going to send the other half of the values to another process, to process 2. Okay. So then after this step, right, 0 is going to still have the value 0, 1, and then 2 is going to have the values 2, 3, and then 2 is responsible for doing the scatter in this little hypercube. 0 is responsible for this hypercube, right, and then 6 is going to take care of this, and then 4 does that one, right? And then in the final step, then of course you just have all of these processes 0, 2, 4, 6, right? They're just going to send to their partner. Okay, so now the cost for doing this, right? So so here the messages that you send in different phases have different sizes. Okay, because for example, in the first phase, right, 0 is sending 4 messages to process 4, right? In the second phase, 0 is sending two messages to process 2, right? And then 4 is sending 2 messages to process 6. Okay, so the size of the messages keeps decreasing over time. Okay, the first message has size p over 2, right, where p is the number of processes. And then on the next phase, they have size p over 4, and then p over 8, and so on. Okay, so so therefore the total cost to do this is we have log p phases, right? And in each phase, the size of the message that you're sending is actually is going to be like this, right? It actually should be something like log p minus I. Okay, but anyways, the sum works out to be the same. And so if you add this up, then you get this expression over here. Okay. Right. So that's for the scatter operation. For the gather operation, that's just exactly the opposite of scatter. Right. So for the gather, imagine that you start in this state, right? And then now you just reverse all of the steps for scatter. Okay. So instead of 4 sending to 5 in the scatter, right, 5 sends to 4, 1 sends to 0. Okay. So then after one step, you're in this configuration, right? And then on the next step, we're gonna send, we're gonna reverse all of these edges, right? And then you're gonna end up in this configuration. And then finally, you're gonna 4 is gonna send to 1, right? And then you're gonna end up here. And now you've finished your gather. Okay. So gather is just exactly the opposite of scatter, and so therefore it also has the same cost. Okay, so next we're going to do this thing called all-to-all personalized broadcast. Okay, so what this means is so now so this is different from the all-to-all broadcast. Okay, this is all-to-all personalized broadcast. So in all-to-all broadcast, each node has a value, and it wants to send that single value to all of the other processes. Right, so all the other processes get the same value from one particular process. Okay, now in all-to-all personalized, right, what's going to happen is each process has a different value that it wants to send to all of the other processes. Okay, not the same value, but different values to all the other processes. Okay, and all processes want to send these different values to all the other processes. Okay, so that's the all-to-all personalized problem. Okay, all right, so so to see how this is going to work, so we're first going to do this on a ring. Okay, so on the ring, in the first time step, right, so 0 has messages that it wants to send to all the other processes. Okay, and the way we're going to represent that is we're going to write these things in the curly braces. So 0, 1 is the message that 0 wants to send to 1. Okay, 0, 2 is a message that 0 wants to send to 2, right, and so on, right? And then here 1, 2 is a message that 1 wants to send to 2. Okay, and then 1 also wants to send a message to 3, to 4, to 5, and to 0. Okay, so 1, 0 is a message that 1 has for 0. Okay, so if you look at if you look at these dotted arrows, which are marked by the 1. Okay, so now these are the messages that you send in the first step. Okay, so in fact 0 is going to send 5 messages in the first step. Okay, 1 is also going to send 5 messages in the first step. Okay, so every process is going to send to the next process in the first step of the algorithm. Okay, and it's going to send p minus 1 messages. Okay, now in the next step, right, so that's going to be given by these lines marked 2 over here, right? So this is for step number 2, and this is for step number 2, 2, and 2, right? What's going to happen is that, well, in step 1, 0 sent a message to 1. Okay, so now 1 has the message that 0 wants to send, so 1 can just keep that. Okay, it doesn't need to pass that on anymore, right? Likewise, 1 sent a message to 2, and 2 can just keep that message, right? It doesn't need to send that to anyone else. Okay, so therefore, on the second time step, let's see. So So 0 has received these messages from 5, right? So 5 has messages for 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, right? 0 is going to keep the message from 5, okay? But it's going to pass the other messages on to the other processes, okay? So therefore, on the second time step, 0 is going to send the messages from 5 to 1, to 2, to 3, to 4, okay? 1 is going to pass, is going to keep the message that 0 sent to 1, okay? So it's going to keep this message, but it's going to pass the other messages from 0 to 2, and 0 to 3, and so on. It's going to pass those onwards to process 2, okay? Process 2 is going to send the messages that 1 is sending to 0, 1 is sending to 5, and so on, okay? So basically, in every time step, right, you receive some messages for yourself, right? And then you're going to keep that message and then pass the remaining messages on to the next node. Okay, so then, so then altogether, this is, if you have p processes, it's going to take you p minus 1 steps, okay? Because in every step, you go one edge along the ring. Okay, and and the cost of this is that each time, so in the first time step, right, you're sending p minus 1 messages. In the second time you send, it's going to be p minus 2 messages, because you keep one of the messages that was destined for you. Okay, in the third time step, you send p minus 3 messages, and so on. Okay, so in general, in the ith time step, you send p minus I messages. Okay. And so the ith time step takes, the time for the ith time step is like this, okay? And then we need to sum this up for all p minus 1 steps, okay? So, and so the sum is basically, we're going to end up with something which is quadratic in p, okay? All right, so next we're going to talk about all-to-all personalized on the torus. Okay, so again, a torus is just a mesh where the first and last processes are connected. Okay, so the way this works is that so initially each process has a message for all the other processes. Okay, so 0 initially has a message for for itself, but also for 1, 2, 3, 4, 5, and so on. Okay, 1 has a message for process 0, for process 1, 2, 3, and so on. Okay, so every process initially has a message for all the other processes. Now we're going to do this algorithm in 2 phases. Okay, so in the first phase, let's see. In the first phase, we're going to do all-to-all personalized on the rows. Okay, and then in the second phase, we're going to do all-to-all personalized on the columns. Okay. Now, what data are we going to send in the first phase? Right. So we know that we're doing all-to-all personalized on the rows, but what we want to do, what we want to accomplish in the first phase is that we want to get all of the data that we need to send in the second phase. In the first phase. Okay. So we want the first phase to produce for each process all of the data that it needs to send in the second phase. Okay, so what is the data that each process needs to send in the second phase? Okay, in the second phase, we're doing all-to-all broadcasts in the columns. Okay, so therefore, each process needs to get all of the values that are going to be sent to the other processes in its column. Okay, at the end of the first phase. Okay, so for example, 0, after the first phase, 0 needs to get values that are being sent to the processes 0, 3, and 6. Okay, so you see that 0 has gotten all of the values that anybody in its row wants to send to either 0 or to 3 or to 6. Okay, so you take the processes on 0's row, which are 0, 1, 2, right? And all of the messages from 0, 1, or 2 that is destined for 0, 3, or 6, right? You want 0 to collect all of that data by the end of the first phase. Okay, likewise, for, let's say, node 3 over here, right? So it wants to collect all of the data from the nodes in its row, right, which are destined for its column. Okay, so it's going to take all the data from 3, 4, and 5, which are destined for either 0, 3, or 6. Okay, and then 6 is going to take all of the values from either 6 or 7 or 8, which is destined for 0, 3, or 6. Okay, so yeah, so that's what you want to accomplish, and so so you're going to do that by doing an all-to-all personalized broadcast. First of all, on the rows. Okay, so in the first phase, you do all-to-all personalized broadcast on the rows, right? And then after that, you're going to do all-to-all personalized broadcast on the columns. Okay, because yeah. Okay. So then the cost for doing this is that, let's see. Okay, so we're going to be sending, okay, so the amount of data that you're sending, right? When you do the all-to-all personalized on the rows, right? So you're sending m times p amount of data, right? Because you know, you have different messages for each other process. Okay, so that's m times p amount of data, and you're sending this to root p number processes. Okay, so yeah, so that's for the first phase, and then for the second phase, you're also sending m times p amount of data. Okay, and you're sending this to root p processes again. Okay, so right, so it should be, I think it, I should have the 2 out here. Okay, so yeah, so the 2 is not over here. Okay, yeah, so then the total amount of time this is taking is basically, it's going to be this expression over here, the TS plus MP times TW, right, times, we know that the amount of time to do all-to-all personalized broadcasts to K processes, right? So from this thing over here, we know that the cost is going to be just multiplied by K, right? So here we're broadcasting to root P processes, so we're going to multiply this by root P, okay? And then you need to do two phases of this for the rows and the columns, so that's where the 2 comes from. Okay, so next we're going to do all-to-all broadcast on the hypercube. Okay, so for the hypercube, each node is going to start with values that it wants to send to all the other nodes on the hypercube. And the way we're going to do this is that we're again going to do these exchanges along the different dimensions. Okay, and the order that we visit the dimensions is just the order of the digits of the binary representation of the nodes. Okay, so we first go with the ones digit, right? So here, what we want to do is, well, 0 has values for all 8 nodes, right? For all 8 processes. Okay, now what it wants to do when it exchanges values with 1 is it wants to take the values that are intended for this phase. Okay, so 1 lies in this phase, right? So now 0 wants to take all the values which are intended for that phase, and it wants to give it to 1. Okay, likewise, 1 wants to take all the values, so 1 has values for every process, and in particular, it has values intended for this phase. Okay, so 1 is going to take all those values and pass it on to 0. Okay, so the same thing between 2 and 3. Okay, so 2 is going to take all of the values intended for 3's phase and give it to 3, and 3 is going to take all the values intended for 2's phase and give it to 2. Okay, so you see that after you do this, right, then by the time we start the second step, you see that each process, right, for example, process 1 over here, right, it's got all of the values intended for its phase, 1, 3, 5, 7, right, which either come from itself or from process 0. Okay, likewise, process 0 has all the values for its phase, 0, 2, 4, 6, right, either from itself or from process 1. Okay, and the same thing for all of the other processes, right? So now, again, we've basically cut this problem in half. Okay, so now we have the left face and the right face. So you cut this problem in half like this, right? And now we can just focus on doing all-to-all personalized broadcast in the smaller hypercube, right? In the left hypercube, and in parallel, we can do all-to-all personalized on the right hypercube. Okay, so the way that you, so let's go one more step, right? So on the next step, right, we're going to be exchanging in this direction, the direction for the second most significant digit, right? And what you want to do is that you see that currently 1 has values intended for both 1, 5, right, and also 3, 7. So 1 wants to take all of the values intended for this 3, 7 phase and give it to 3. Okay, and 3 wants to take all of the values intended for the 1, 5 phase and give it to 1. Okay, so basically 3 is going to give, so let's see. Okay, so 1 is going to give these values, right, which are intended for the 3, 7 phase. It's going to give those to 3. Okay, and 3 is going to take all of these values, which are intended for the 1, 5 phase and give it to 1. Okay, and yeah, and similarly for 5 and 7, and then 0, 2, and 4, 6. Okay, so then after you do that, you've again decomposed the problem into 2 parts. Okay, so then we just we keep doing this, and so the total number of steps we take is log p, right? And in each step, you have to send half the data, right? So for example, in the first step, right, 0 had to send half of the data, the data for this phase, right? So half the processes are in that phase, so you have to send half the data in each step. Okay, so then so the amount of data is going to be just p divided by 2 in each step, and then we have log p steps. Okay, so the total time is going to be this value over here. Okay, so so basically the cost over here is something like, so if we treat all these values as constants, then the cost is something like on the order of p log p. Okay, so now let's look at how good this is. Okay, so let's think about this. So each process is going to receive p minus 1 pieces of data from the other p minus 1 processes, right? So yeah, so each process receives this amount of data, right? And how far did this data have to travel? Well, on average, you're going to receive data from, since you're receiving data from all of the other processes, right? Then the average distance that the data had to travel is basically log p divided by 2, right? Because the diameter, the farthest node, the farthest distance that you would receive a message from is log p. Okay, so the average distance that you receive a message from is going to be log p divided by 2. Okay, so you receive p minus 1 pieces of data, and the data traveled a average distance of log p divided by 2. So the total amount of communication, okay, which is equal to the size of the data that you received times how many edges it had to go through, right? So the product of these two things is p times log p, is on the order of p times log p. Okay, now we know that the number of, let's see, so the number of edges, or sorry, the number of links in the hypercube is also p times log p. Okay, so therefore a lower bound on the communication cost is going to be the total amount, the total volume of the communication that you're doing, right, divided by the number of edges. Okay, so this is going to be m times p minus 1. Okay, so yeah, whereas the amount of time that we spent is basically m times p times log p. Okay, whereas for the lower bound, the minimum amount of time you should be spending is something like m times p. Okay, so you see that this cost over here is basically a factor of log p larger than the optimal cost. Okay, so this is saying that this algorithm that we have currently is not optimal. Okay, so let's see if we can improve on this algorithm. Okay, so we're going to look at a different algorithm for all-to-all personalized broadcast on the hypercube. Okay, and so here, so in the previous algorithm, right, we took log p steps. So you just took a few steps. But for each step, you had to send a lot of data, right? You had to send half the data. Okay. Now here, instead, we're going to take we're going to use a different algorithm, which is going to take many more steps. In fact, it's going to take p-1 steps. Okay. But in each step, each node is only going to send one piece of data. Okay. And we're going to see that this algorithm is going to be more efficient. And in fact, it's going to meet the lower bound on the communication. So what we're going to do is we're going to run for p-1 steps. Okay, and in the jth step, every process is going to send to somebody else. Okay, every process I is going to send to another process. So which process is it going to send to? Well, process I is going to send its data to process I XOR j. Okay, so for example, if you look at, let's say, step 7, okay? So step 7, the j is going to be equal to, if you write j in binary, right? So 7 equals 111, oops. In binary, right? So that means that each I is going to be sending to I XOR 111. Okay, so it's going to flip all its bits, basically. Okay, so that means that, for example, 0, right? 0 XOR 111 is going to be 7. Okay, so 0 is going to send to 7. Okay, 1 XOR 111 is going to be 6. Okay, so 1 is going to send to 6, 2 is going to send to 5, right, and so on. Okay, so that's in the 7th step, right? In the 6th step, right, we would be I would be sending to I XOR 110. Okay, so for example, 2, right, would be sending to so 2 is going to be 010. Right, and if you XOR this with 110, you're going to get, what do we get? We get 100, okay, right? So then 2 would be sending to 4. Okay, so 2 is going to send to 4 like that. Okay, and then what do we have? We have, let's say, for example, 3, right? 3 would be sending 011, right? XOR 110 would be equal to, what do we have here? 101. Oops. Okay, 101, which is 5. Okay, so then 3 would be sending to 5, like that. Okay. All right. Now, when also when you do the sending, okay. So so for example, when when 0 tries to send to 7, okay, or when 1 tries to send to 6, okay. So we're going to make sure to use the E-cube routing. Okay. So remember that the E-cube routing. So we talked about this when we talked about communication. So the E-cube routing in a hypercube is that we're going to order the dimensions in some way. Okay, so let's say from least most significant digit to the most significant digit, right? We're going to order the dimensions in this order, right? And then we're always going to send the messages along these dimensions, okay, in that order. Okay, so for example, if we order them like XYZ, all right, we're always going to send in the order XYZ. You can't send in you can't send in, let's say, a direction Y first and then send in X. Okay, so we're going to use this E-cube ordering, and then every process is going to send to someone else. Okay, now it turns out that because there's so many edges in this hypercube, okay, it's going to turn out that in each time step, okay, when I needs to send to the XOR of J, right? Then so in each time step, we actually have P messages which are being sent, right, simultaneously. Okay, but because there's so many edges in the hypercube, all of these P messages can be sent without any congestion. Okay, meaning that each edge will only be used twice, once in each direction. Right? We're not going to have any edges where many processes are trying to use that edge at the same time. Okay, And since since each process is only sending one message, right, and then each edge is only being used for two messages, right, so one message in each direction, then the amount of time to send those messages on each edge is just going to be 2 times m times tw. Okay, so therefore the total amount of time is maybe there should be like a 2 over here, okay, because we're sending 2 messages per edge. Okay, so the congestion on each edge, sorry, is 2. Okay, and then yeah, so we can do all p sends. So each time step involves p sends, right? And we can do all p sends concurrently, and the total amount of time to do all p sends is just this expression over here. Okay, and since you need to run p minus 1 phases, right? Then the total amount of time is going to be the product of these two things. Okay, so this is going to come out to m times tw times p minus 1 basically, right? So now if you compare that to the lower bound on the cost, right? So the lower bound on the cost was this thing over here. Okay, so this shows that this new algorithm based on the XOR routing, right? But based on sending to your XOR, right? This is within a factor of 2 of the optimal cost, right? And so this is actually better than the first all-to-all personalized hypercube algorithm that we had. Okay. All right. So next, we're going to move on to the final problem, which is how to do a circular shift. Okay. So a circular shift, what we're trying to do is, if you're trying to shift by k values, then every process, so process I should send its value to process I plus k. Okay. However, because it's a circular shift, then if I plus k is actually larger than the number of processes, then the message should actually end up at I plus k modulo p. Okay, p is your number of processes. Okay, so for example, suppose you want to do a circular shift by 5. Okay, so what that means is that 0's message should end up at 5. Okay, so for example, here 5 has the message from 0. Okay, 1's message should end up at 6, right? 2's message should end up at 7, and so on. Okay, now if you take one of these processes like 14, okay, if you shift by 5, then you need to go 1, 2, 3, 4, and 5. Okay, so this is 1, 2, 3, 4, 5 processes. So therefore 14's message should end up at 3. Okay, so that's what a circular shift is. Okay, so you just you pass your message forward by k steps. Okay, for some k. Okay, so now the question is, how do you do this in a mesh? And what we're going to do is, okay, so to do the circular shift, we're going to shift both in the x and the y directions. Okay, so if you shift in the x direction, right? So if you shift by 1 in the x direction, then you're basically then you're shifting the message by just a distance of 1, right? So so if you do a shift in the x direction, then 0's message gets to 1, 1 goes to 2, and so on. Okay, so this represents a shift of by 1. Okay, now on the other hand, if you shift in the y direction, okay, then 0's message is going to end up at 4, right? And 4's message is going to end up at 8, and so on. So this is actually a shift by 4, right? So in fact, if you have a mesh which is size root p by root p, right, then each time you shift in the y direction, you're actually shifting by root p. Okay, so now if you want to do a total shift of k, then what you can do is you can do k divided by root p shifts in the y direction. Okay, you do the floor of k divided by root p shifts in the y direction. And so this is going to move you basically k divided by root p times root p, right? That's going to move you this number of steps. And then this is not quite equal to k yet because you're doing this floor operation. And so you need to add to this k modulo root p. Okay, and now this is going to be equal to k. Okay, so this is how we're going to do the shifts. Okay, we're going to do we're going to do this number of shifts along the y direction, and then we're going to do this number of shifts along the x direction. Okay, so now so let's first consider shifting along the x direction. Okay, so as an example, suppose you're trying to shift by 5, and you're shifting on a 4x4 mesh. Okay, so this means that you need to do a shift of 1 along the y direction, which actually moves you a distance of 4, right? And then you also need to do a shift by 1 on the x direction. And so in total, you're moving 4 plus 1 equals 5. Okay, now when you do the shift on the x direction, okay, so if you do the shift on the x direction, then imagine that there's sort of this little ring over here, right? And then you sort of, you just shift everything by 1 along the ring. Okay, then what's going to happen is that 0 is going to move to 1, 1 is going to move to 2, 2 to 3, and then 3 is going to move to 0. Okay, so then after the shift, you have that 3 moves to 0. Okay, so now everything is okay, except that 3 should not be at 0, right? Because you want to actually move 3 to 4. Okay, and likewise, when you shifted, if you shift by 1 on the second row, right? Then you actually have 7 is going to move to 4. But you don't want that. You want 7 to move to 8, right? And likewise, you want 11 to move to 12. And you want 12 to move, and you want 15 to move to 0. Okay, so you see that here, everything, all of these values here are off by 1. Okay, you want 3 to actually move up 1, and you want 7 to move up 1, and so on. Okay, you want something like this. Okay, so therefore, after you do the shift on the x direction, you need to do another shift on the y direction just to move the 3 to the right place, the 3, 7, 11, and 15 to the right places. Okay, so then after that shift, right, then after you do a shift by 1 on the x direction, and then also another shift in the first column, right, then we actually have moved everything over by 1, right? So 0 has moved to 1, 1 moved to 2, 2 moved to 3, and 3 moved to 4 over here, right? And so on. Everything has moved by 1. Okay? All right, so this is our shift in the x direction, right? We just need to do one shift in the x direction, right? And then after that, we're going to do another shift in the y direction. Okay, so every column is going to do a shift, right? And then after you do that, right, we're going to end up at this this configuration over here. Okay, so here everything 15 is going to move up one row, right? So that corresponds to actually a shift of 4, right? And the 3 is going to move up by 1 row, which also corresponds to a shift of 4, and so on. Okay, yeah. So so the algorithm is to first shift along the x dimension. Okay. However, for each x shift, right, you need to do one of these. You need to do another shift on the first column to compensate for the fact that this final value over here should actually move up 1 row. Okay. And then after you've done all the shifts in the x direction, then you can shift along the y direction. Okay, now you notice that the total number of shifts that you need to do in either direction, either x or y, is root p, right? Because the size of this grid is simply root p by root p. Okay, so at most you can be doing root p shifts in the x direction and then root p in the y direction. Okay, and each shift, we can do all the shifts along all the rows or all the columns simultaneously. Right, because all the shifts are using different edges. Right, there's no congestion when we do a single shift in the x or y direction. Okay, so each of the shifts costs you ts plus m times tw time because there's no congestion. Okay, and since you're going to shift at most root p times in the x direction and the y direction, then the total time is going to be this. Okay, it's going to be 2 times this thing times root p. Okay, so one final algorithm, which is how to do a circular shift on a hypercube. Okay, so what we're going to do here is that we're going to use, so remember that from an earlier lecture, we had a mapping from a ring into a hypercube. Okay, and the way we did the mapping was using these gray codes, right? So remember the gray codes were, so a k-digit gray code is just, it's an ordering of all of the k-digit binary numbers such that consecutive numbers differ in only one digit. Okay, right, so that's the gray code, and we have this recursive construction for the gray codes. Okay, now when you map this onto, and the way that you map a ring onto a gray code is that for the ith node on the ring, right, you just compute the ith gray code number. If you have, let's say, 2 to the k processes, okay, then we're going to map this onto a k-dimensional hypercube, right? And you're going to take the ith process from the ring, and you're going to map this onto the ith value in the k-digit gray code. Right. So if you want to look this up, you can go back to one of the earlier lectures where we actually covered this in more detail. Okay. But anyways, we have this mapping from the ring to the hypercube, and this mapping has some properties. Okay. So for example, one property is that so you can try to check these properties or try to prove these properties. Okay. They're not hard to prove. So one property is that if you take any I larger than 0, okay, then any two nodes which differ by 2 to the I value in the ring, right, they're going to be mapped to nodes which are distance 2 apart in the hypercube. Okay, so for example, if you take two nodes, 2 and 6 in the ring, right, so they differ by a power of 2, right, they differ by 4, okay, and node 2 is going to get mapped to, so if we have 8 processes, then node 2 is going to get mapped to 0, 1, 1, in the hypercube based on the gray code ordering, and 6 gets mapped to 1, 0, 1. Okay, and now these two nodes in the hypercube, right, they differ in 2 digits, right, in the most significant and the second, in the first and second digits, and so their distance is going to be 2 in the hypercube. Okay, and it turns out that this holds for any I larger than 0. Okay, if two nodes differ by 2 to the I, then they're going to differ by a distance of 2 after being mapped to the hypercube. Okay, the other property is that if you have neighbors in the ring, okay, then they're going to be mapped to neighbors in the hypercube. Okay, because remember the main property about the gray code ordering is that if you take 2 consecutive values in the gray code, right, they only differ by 1 digit. So if they only differ by 1 digit, then these two numbers are going to be neighbors in the hypercube. Okay, so we have these two properties. Okay, this property over here and this property. Okay, so now we're going to use these properties to see how to do a shift operation. So suppose you're trying to do a shift by k. Okay, then first of all, we're going to write k out in binary. Okay, and then we're going to shift in the along the dimensions with the 1 digits. Okay, so as an example, suppose you're trying to shift by 5. Okay, so then you write this in binary, which is 101, right? And the dimensions with the 1 digits are the 0th dimension and dimension 2, right? So then we're going to do a shift of 1. And then we're also going to shift in the 2 dimension, which corresponds to a shift by 4. Okay, so then altogether we've shifted by 5. Okay, so so in each dimension which is different from 0. Okay, so for example, in this dimension, in dimension 2, okay, if we want to shift by 2 to the I, right, then by this property over here, right, when you want to move when you want to move every node up by 4, right, by 2 squared, okay, then you only need to then the distance you need to travel in the hypercube is just 2. right? Because, for example, if you want to move 2 to 6, okay, you just need to travel from this node, right, 0, 1, 1 to 1, 0, 1. Okay, so that's a distance of 2. Okay, so every time you have one of these dimensions different from 0, and if you have a 1 in that dimension, then you only need to take 2 steps. Okay, and then we also need to shift in this 0 dimension, and here you only need to take 1 step, okay, by this property over here. Okay, so therefore, the total number of steps that you need to take is that, well, we have, at most, we need to shift along all of the dimensions, right? So they're log p dimensions. So at most, all of these things are 1s, right? So then we need to shift in every dimension. So they're log p dimensions. Shifting in each dimension other than the first one is going to take us 2 steps, right? And then shifting in the final dimension just takes you 1 step. So altogether, this is going to take you 2 times, right? And when you shift, right, you're just going to move. There's no congestion for the shift, right? And so you can do the shift in this amount of time, right? And then in total, you need to shift log p times for log p digits. Okay, so the total amount of time is this expression over here. Okay, so that's all we have for how to implement these collective operations. Okay, so then next time we're going to talk about how to program in the shared memory environment using a language called OpenMP. Okay, so see you all next time.